thank you very much for the introduction, for the invitation. And so I'm going to talk to you about the things that I've been doing for some years, namely studying phase diagrams of patchy particles. In fact, in this talk, I will concentrate just on a part of this work, on the part that I think it's most fitted to the subject that we are dealing with in this conference. So this work has been done in collaboration with a lot of people. So on the theoretical part, Paulo, Margarida, and Daniel Laceres from Lisbon, and now Daniel is in Bayreuth. And then the simulations were done in off-lattice models of patchy particles with a group in Rome, and of course they also contributed a lot to the theory. And in some lattice versions of the patchy particle models, we had a collaboration with a group in Madrid. So the outline of this talk is the following. First, I will introduce you patchy particles, I think the simplest version of patchy particles, and then I will show you some results of the calculation of the phase diagrams for these simple patchy particles, where this notion or this phase of empty and percolated liquid appears. And then I will try to convince you that one route to get this interesting phase is to somehow make more complex the patchy particles by saying that you have several types of patches, of different patches on the particles, and then to go to binary mixtures of patchy particles. So I must say from the beginning, just to not be confused with the previous talk, that I'm going to deal only with the low density part of the phase diagram. So I will only study gas and liquid phases, orientational disorder and positional disordered phases. Okay, so that's to be clear from the beginning. So patchy particles. So there are several ways of realizing patchy particles. This is the simplest one. So you just pick hard spheres, and then you place on the surface of the hard spheres what you can call bonding sites or patches in an integer number. So here you have several examples of two patches, 3 patches, 4 patches, 5 patches. And then you have to make pair potential between these particles, and usually you have the hard sphere part, and then you have the patch part. And there are several ways of implementing this, but in the end, you can always describe it this way in the first approximation. So if your 2 spheres or two particles are far apart, you just have a hard sphere system, nothing happens. And however, if you put these particles close together so that 2 patches overlap, then you say that you form a bond between the patches. And this means that the energy goes down by some amount. And of course, this means that also the entropy goes down by some amount, because now this second particle cannot explore the whole volume. And the entropy will be proportional to the logarithm of this volume that we call the bonding volume, which is basically the volume that a particle can explore, or a hard particle can explore, while still connected to the other one by the patches. Of course, these are small quantities, so this volume is small when compared, for instance, to the volume of the spheres. It's really small. And you can immediately see, using this picture, that if you go to low temperatures, these particles will self-assemble in clusters. So the energy will be minimized just by making connections between the particles, so particles will form clusters. Okay, so in this low density limit with particles with few patches, we impose also these geometric restrictions that I can develop more if you want. But basically, this comes from the fact that the patches are very small and are randomly or like this distributed over the sphere in particular places, the further apart that you can put them. So these are results from the group in Rome around 10 years ago, and they calculated the phase diagram of these particles using Monte Carlo simulation and Wertheim's theory. And they calculated 4 different values of the number of patches in the particles. So for 3 models, 3 different models. And so this is one of the figures. This is theoretical results, but it could be also, so the simulations fit over these results. And here you have, for instance, this line is the binodal in the temperature density phase diagram. So this means that here inside the green line for this m equal to 5 model, you have a liquid vapor coexistence, and here you have a liquid, a stable liquid. And you immediately see that what happens when you decrease the number of patches is that this line shrinks, okay? So you start having here in this region liquids, stable liquids, at lower and lower densities. So they do not coexist with the vapor, they are really one-phase liquids, and you can get these liquids at lower and lower densities if you decrease the number of patches in your model. So now these lines here that you call percolation. So this means that below these lines you have percolation. So as I told you, so this system self-assembling in clusters, and below these lines you have an infinite cluster in your system. So that's why the people that did this work call these liquids empty liquids, in the sense that you can get liquids at lower and lower densities, and also network liquids or gels or candidates for equilibrium gels, because the system has already percolated. Of course, you have a limit in this type of model because you cannot go below 3. Okay, so you have 3 particles. If you go to 2 patches per particle, the only structure that you get self-assembly is chains, and chains, so they do not percolate, they do not phase separate, so it's not interesting for this purpose. So the next idea was how can we go from 3 to 2? Okay, and of course the simplest way was to say, let's make a binary mixture. I'm going to tell you about this in the end of the talk, of particles with 3 patches and 2 patches, and let's decrease the number of particles with 3 patches. You can go to this theory. So in this theory, this number of patches per particle is a parameter, and you can plug in the theory the number of patches that you want. Okay, so even a fractional number of patches. And if you do that and calculate the phase diagram, what you see is that you are shrinking continuously the phase diagram. So open up here the possibility of having liquids at lower and lower densities. And so the problem is that, of course, this is a mean number of patches per particle, and in this calculation, and I will come to that in a moment, in this calculation, they have neglected the entropy of mixing, and you'll see that it's important, the entropy of mixing. So you can get low-density equilibrium gels or empty network liquids here in the phase diagram if you go to this limit, the limit where the number of patches per particle goes to 2, kind of chain limit. You cannot do it in the chain limit because you lose the network if you go to chains. But if you approach 2 from above, you can reach try to reach this limit, and you get this empty network in this phase, in this region of the phase diagram. So how to do it? How to reach these limits continuously? So our idea was to change a little bit this model of patchy particles by considering that the particles can have dissimilar patches, so you have several types of bonds. And I will show you that we can really increase this region where you have empty network fluids if we do this. And then also the idea of making binary mixtures of patchy particles with 3 and 2 or 4 and 2 patches. So one of the components has 2 patches. Maybe in this way we could reach also this limit. And I will, in the last part of my talk, I will discuss this and the problem of entropy of mixing. So this is the generalized patchy particle model that we invented. So we have, again, hard sphere, and we have several patches, but now the patches are of 2 types. So we have 2 patches A, and you have patches B of, well, I don't know, N patches. So here is an example with a patch B. And so what happens immediately here is that you increase the number of parameters of your model. So now, instead of having one energy scale and one, say, length scale or bonding volume, you have three types of bonds, AA, AB, and BB. So now you have three energy scales, and you have three bonding volumes. So, and you can play with these parameters and see what happens. So you can play in the simulations, in the theory, and in fact, we did it theoretically in these papers, and we calculate phase diagrams for all possible combinations of these parameters, especially we didn't play a lot with this bonding volume, especially the energy parameters. And in the end, we found out that if we choose these parameters in a certain way, we can reach this limit in a very interesting manner. And so the choice of these parameters is the following. So that's to reach this limit. So let's put the BBs equal 0. This means that you don't have this type of bonds. So you just eliminate this type of bonds. And now you restrict yourself to this relation between the energetic parameters of the other two bonds. Epsilon AB is lower than epsilon AA over 2. Why? We do this because you can show, it can be shown very easily, that if you do this, then the ground state of this system is infinitely long chains formed by AA bonds, sequence of AA bonds. So you have a ground state with infinitely long chains. And now you can guess, I mean, we could go to the simulations and to the Wertheim's theory and calculate the phase diagram on this, and I could show you in a slide where they, how they are, and I'm going to show you in a few slides, but first let's think a little bit about this, okay? So suppose now that you are a very low temperature and you are a very long chain. So these red spots here are the patches, and so they connect to each other and you start to form very long chains. And now you increase a little bit the temperature, you have temperature fluctuations, and mainly two things can happen in the first approximation. The first thing is that you can break a chain. So if you break a chain, so your energy goes up by epsilon AA. But you create two defects that we call also the end defects, which are A patches that are not bonded. Okay? So each unbonded patch or end defect makes the energy grow by this amount, okay, here. Of course, you also have an entropic effect. So entropically, it's favorable to break the chains. You can explore more volume, and you can theoretically, but I mean, you can say that the entropic gain of creating one end defect is this one. Is here, it's related to the volume of AA and to a reference volume that is basically twice the excluded volume of two spheres, or the reference, or the excluded volume of the reference system. And then you have another possibility. Once you have break a chain, you can pick one of these ends, okay, and then connect it to a B to make AB bond. And so you create a branched structure, so Y or a T junction, and you have so we call a junction defect. And the energy of this junction, relatively to the ground state, is epsilon AA over 2 minus epsilon AB. It's still positive, so it's energetically, it costs to create a junction, but this cost is less than the cost of creating an end. So junction defects are energetically favorable relatively to end defects. And you can also estimate what is the decrease in entropy or increase or variation in entropy when you create a junction. And you have here an increase because to create a junction you have to create an end also. But then you have here usually, for most models, a negative part. So in principle, junctions are entropically unfavorable relative to ends. So you have here a competition between two types of entropic defects, in the sense that they just appear when you have some temperature, and they are not energetically favorable for the system. And this competition will set the phase behavior. And the phase behavior can be calculated with the theory, and you can pick the theory and make an analytic expansion for low density systems and for low temperature, that means strong association or strong self-assembly between the particles, and you get a very simple expression. So you have, for instance, for the pressure, you have two positive terms. One just counts the excluded volume, the excess excluded volume for the reference system, and then you have the density of end defects and the density of junction defects. And you have here this minus sign, so it seems that these junction defects will make an effective attraction that promotes a phase separation. But of course, then you have the density dependent of these two densities of junction and defects. This rho is the total density, and you see that there are exponents not very usual. And this is really the sign of self-assembly, these 1/2 and 3/2. So you have this density dependence that is different from the usual. And not surprisingly, what happens is that you get phase diagrams different from the usual ones. So in fact, you can have several types of phase diagrams depending on the values that you choose for the volume of the bonds and the energy of the bonds. For instance, if the entropy of the ends is much larger than the entropy of the junctions, more than 3 times, and this is usually the case for most of the models that we have calculated and simulated, and you have the following phase diagram. So if the energy cost of the junctions is not too high, up to 1/3 when related to epsilon to the energy cost of the ends, you have one critical point and a reentrant liquid binodal. And if it's too high, the energy cost of the junctions, so that those attractions promoted by the junctions are not enough to make a liquid-vapor coexistence, so you have no critical point. So this is the phase diagram. So this is temperature and this is density for these models, 2A and B patch particles, where you have 2A's and then B's, and 9 B's, sorry. You are on this case when you fix the bonding volume so that you are on this case. And you have this energy cost for the junctions. And so these points are simulation results. And what you have is that, so they correspond to coexistence points. So here you have a gas coexisting with a liquid. And down to here, everything is normal, as usual in the liquid, more simple, the simplest liquid vapor phase diagrams. But still, at low temperatures, what happens is that the liquid binodal becomes a reentrant. It means that the coexisting liquid starts to decrease its density. And so here in this region, you have a liquid of very low density, so it's not a gas. So the gas is really at here almost 0, and a percolated liquid, as you can show in simulations and in theory. So in this case, in this model, you have opened up possibility of having empty liquid equilibrium gel even more than in the case of the simple patchy particles. I mean, it's even more striking or different when you go to this case. So this case means that the junctions are entropically, have more entropy than the ends. So this means that they are also entropically favorable, the junctions. You can only do this in very artificial models where you have to have lots of deep patches on the particle and have a very large AB. In fact, we are only able to do this on lattice versions of models of patchy particles. And now what happens is that there is a region here for intermediate energy costs of the junctions. You have 2 critical points and reentrant liquid and vapor binodal. So these are the simulations for FCC patch lattice model with 10B patches. And here what you do is that you go from 1/2 to 0 in this relative cost of energy of ABs and AAs. And what happens is that the phase diagram shrinks, but in the previous case, you should stop here at 1/3, and here you see that you can go to lower values of this ratio. And so, and if you do the calculation theoretically, you get single particle system with two critical points, an upper and a lower critical point. You can also get this type of phase diagrams in some extensions that we did of this model. So the first one was to enhance the possibilities of ring formation. So what you do in the simulation to have rings is that you put these two-way patches a little bit off pole. So now there is some tendency to curve, and you can form rings. And in this case, so you can also include the rings in the theory. And in this case, well, you get temperature density phase diagrams with clearly two critical points for all the energy costs of junctions. So you have, these are closed loop phase diagrams of a single component system. And of course, around the lower critical point, what you have is a coexistence between a phase of, a vapor phase formed just mainly by rings, and then a liquid phase, which is a branch structure with junctions. But the vapor phase has a lower energy and a lower entropy than the liquid phase. So you reverse this variation relatively to what happens usually between a liquid and a vapor. And so again, here you have at low densities, you see here you have a liquid or percolated liquid, and you have no gas, and so you have an empty liquid in the sense that I explained before. Finally, in this part of the 2A NB patchy particle model, we make another extension, was just to see what happens if you, instead of having two types of patches, you have three types of patches. Can we get the same type of phase diagrams that we obtained for 2A and B patchy particles? And the answer is yes. If you have three non-zero energy scales, you can select this energy scale so that you get just the same phase diagram. So here is an example. Suppose that you just select to make AC, AA, and BC bonds. If these parameters, energetic parameters, follow this relation, then you have your ground state is AC chains, so chains formed by continuous connections of AC bonds, and you have BC junctions, and you pick up times theory, and you just expand the pressure, and you get a similar expression than before. So you have a hard sphere part, and you have two terms that come from the two types of ends that you can create, and then the traction from the junctions. You can get, again, this dependence on fractions, on fractional exponents in the density here, here, and here. And then you can work out the phase diagram, and you can see that depending on the choice that you do of the parameters, you can have parts. You can have phase diagrams with no critical points, and you can have phase diagrams with liquids binoculars. So to finish, I want to go to the binary mixture part. And here, so we studied a lot this system, binary mixture of patchy particles, but here I'm just going to concentrate on this problem of the empty liquid and of the entropy of mixing. So you have two species, so two types of two types of patchy particles, but they have the same diameter. All patches and bonds are equal. This means that the energy and the bonding volume is independent of what patches you are connecting, if you are connecting patches on particles of the same species or different species. And the only distinction between these two species is the number of patches. For instance, in this example, you have one of the species has two patches and the other has three patches. And here you have a kind of picture of what you expect to happen. So you remember that some slides ago I told you that we get this limit of the empty liquid if you have chains and then some branching. Okay, and here the idea is that if you have much more particles with two patches than with three, you can have chains that are connections between these particles, and then from time to time you have branching provided by the three patches, the particles with three patches. So that's the idea, and in fact, again, I will show you this again because this phase diagram is obtained if we neglect the entropy of mixing, okay? As if all the particles would have a non-integer number of patches. So you are, if you want, you are neglecting concentration fluctuations, and you get really an empty network fluid. But the problem is that can you neglect entropy of mixing? Okay, can you neglect the entropy of mixing? And so we calculate really the phase diagrams using Wertheim's theory. So you can include in Wertheim's theory the entropy of mixing. And these are examples of binary mixture phase diagrams for binary mixtures of 3 and 2, and binary mixtures of 4 and 2. And here, let's concentrate here. So this shaded area means the coexistence between the liquid and the vapor. These are temperature concentration phase diagrams. You have fixed the pressure to calculate this area and these lines. And you can see that at this pressure, you can have liquids with fewer and fewer three-patchy particles, when more and more particles, so long chains and some branching, until you go almost to, this is the density temperature projection of this phase diagram, almost to density 0. So if you have mixtures of 2 and 3, this suggests that you can still have this phenomenon of empty liquid in this system. On the other hand, when you go to this type of mixtures, we also calculate for 2.5 and 2.6. So these are lower and lower pressures. Let's concentrate on the lowest pressure, which is this one. And this is not similar to this because you have a kind of bulge here. So this bulge means that when you start to increase the concentration of particles of 2 and start to elongate your chains, so at some point you have a coexistence between two network liquids. Okay, one reaching particles with 2 chains, rich with particles with 2 patches, and another rich with particles with 4 patches. So you have here a demixing transition between 2 network liquids that doesn't appear on this case, 2 and 3. And if you calculate the critical properties of this critical point here, in this figure, so when you compare them with the dotted red line, this dotted red line is what happens if you neglect the entropy of mixing. So what happens that only the mixture with 2 and 3 follows the red dotted line. So only in the case of a mixture of 2 and 3 can you neglect the entropy of mixing. In all the other cases, you cannot do it. For instance, you can look here at 2.5. So if you make a mixture of 2 and 5, what happens is that the critical point that is associated with the liquid vapor phase transition and the network empty liquid is replaced by a demixing position between, and you don't go to, so the density doesn't go to 0. The mean number of patches per particle doesn't go to 2, so you don't have any more this empty fluid regime. Okay, so that's it, and I finished in advance, but okay, that's it. So you can make questions, and thank you very much for your attention. Okay.
So when you talk about these patches, if you look at it experimentally, these are not single locations.
Yeah.
So there's some kind of a spatial extent to these patches.
Yeah.
How would one account for such kind of?
No. I mean, I didn't have the time to talk about everything, but this was part of these results were confirmed experimentally by a group in Milan in collaboration with Rome. So they built up a kind of colloid with DNA, and they have a very short chain. So that's why it's different in the end of the DNA, so that they make a complex DNA that has for instance, 4 arms, and then at the tips of the arms you have complementary strands. But of course, then you have the problem because they explore. They're not fixed. But still, you can more or less some of these results you can reproduce them.
Yes. Okay, I had to wait. Just one question about the theoretical description of these, the phase diagram of these patchy particles in the limit that you have close to 2 patches, but not exactly 2, in which case you can have the chain ends junctions. It sounds in a way similar to the theoretical work of Safran, Tlusty, and Tillman.
Yeah.
And so, could you briefly explain what are the differences and what are the similarities?
The difference is a methodological one. So he just took it out from his head for dipolar systems, and here we went to this liquid state very well established theory, and we did this with 2 patches, and then we derived it, and in the end we got the same dependence on the density and on the free energy. But still we can make a. I mean, if you go to the details of the article of Sam Safran, you have. The entropy is not of the junctions, and it's not very. I don't understand it very well. And here I can understand because I did it all the way down. Okay.
Thank you.
But it's really it's the thing is that we have a more general theories. If you want to compare with the simulations, we can put all the terms, not only the first. So and then we show that the first terms of our theory are equal to those of Sam.
Okay. Thank you.
So these patches are interacting by volume exclusion, or there is an interaction cutoff that you have used?
You have to speak.
So these patches are interacting by volume exclusion, or there is an interaction cutoff?
No. They have some, they could be chemical, they could be DNA, so they are attractive.
No, but in your simulation, what have you used?
In the simulations, so you have a model for the interaction between the patches. So you have to write down. You have 2 particles. Okay, if they are far apart, and if they approach, they cannot overlap. But if the patches are oriented in some way, there is some attraction. So you can implement this very easily and in several ways in the computer simulation, also in the theory. Okay, but the general point is this one. So you have an attraction when the patches overlap, and then you have some bonding volume. So you can still explore, the particles can still explore some volume when they are connected.
Yeah, as far as I remember, one of the sort of primary practical motivations for the system was to essentially optimize to get, for instance, some elastic response with almost no density in place. So, coming back to sort of this application side, what would be your recommendation? What is the right way to?
I mean, I'm not an experimentalist, so I don't know. I can say something, but I don't know. But in principles, yes, you had to go and engineering something like we presented here, so with several types of patches, because these experimental systems that I told you about, they were all done with the same complementary strands, so you have only basically 1 energy scale in this language. So if you go to 2, in principle, you could get rid of the coexistence between a low density colloid and a high density colloid and still have them connected. Okay, but I don't know if someone is interested in doing this. I don't know. Okay.
The range of interactions that you look at here?
No, they're really small. So these patches have to be really small. The range of interactions you're telling me, so they have to be really small. Then I can tell you.
Yeah, so if we are going to increase the range by maybe increasing the strand length or maybe, so then do you expect this to change? And
yeah, I mean, if you increase the energy, if you make them stronger, that's just like changing the temperature, so that's not very important. But if you increase the range of the patches, then what happens is that you don't fulfill anymore these restrictions here. And then you can start to have, for instance, a bond formed by 3 patches, okay? And you can start to have 2 particles that are bonded by 2 pairs of patches, okay? And that changes a lot the phase diagram, okay? But yeah, you're right, and in principle, so you have to design this, so to get these effects, you have to design this very specifically, so, but you're right, there are changes.
Hey. You showed some phase diagram as a function of density, so I was wondering, like, if you superpose a small flow in the system and then bring it back to static position again, do you get a different, different phases?
I mean, you mean induced flow,
Yes.
using flow to induce this self?
Flow, maybe shear flow or something,
flow or
and then...
I don't know. I'm interested on that, but I don't know. Okay, I don't.
Is it in the simulations, are the energies of the bond formation such that they are reversible? Is there a possibility of debonding?
Yeah, I mean, in principle, yes. But of course, they have, I didn't do the simulations, but they have those types of problems at some point. So the energies are so low that everything gets stuck and you don't move it anymore. So they have several tricks to because these are Monte Carlo simulations. So you are not obliged to follow a time. So they can do all the kinds of tricks to make this go to the stable phases. Okay, but yeah, I can show you the papers, but they have to do a lot of tricks because of it.
Okay, so I have a question about the coordination number going to 2 limit. Now,
Yeah.
I guess if you are looking at strictly patchy particles, the phase transition goes away, right?
Yes, when you go to the 2 limit, yeah.
But if you in the earlier sort of version of these models, you had a maximum valency model where you had up to a certain, there weren't patches where you could basically have bonds, but there's a limit on the number of bonds that you could make.
Yeah.
So in that case, is it clear that the same limit applies, or is it something different?
Well, I don't know. I should. I guess yes, but I don't know. So if you do it in another way, so you just limit the number of bonds that you can make and not the number of patches. Mm-hmm. So my fair answer is I don't know. I suspect it's the same because I don't know. Well, the physics should be the same, but
okay. All right. So with that, let's thank speaker again.